we have another very interesting question from a very active student of mine, Tony. So he's also here for me to answer the question, and of course we will also make a video for the rest of us to use. Now, so the question was, how do we find differentiation or derivative of a composite function? How do we differentiate a composite function? The way I've demonstrated it here is a very common way of demonstrating it. So is g of fx. Basically, it means that whatever the function g is, we will substitute fx into it. So the preferred way of really writing it, the way I would like to write it, is g, and the function of g is working on another function, fx. So that's the way I like to write it. So in fact, the variable of g, so the variable of f is x, but the variable of g is the output of fx. Now, so for dealing with this, we use the chain rule. So I'm just going to quickly, through a simple question, a simple example, I'm going to remind you of your knowledge of chain rule. So if we, for example, have a function of x, which is 2, say, x squared plus 5x to the power of 4, then the normal way that we go about this, without taking shortcuts, the normal way that we go about this is that we will substitute, make a substitution, and we make the content of this bracket to be a new variable called u, and hence y would become 2u to the power of 4. Yeah, and so that's sometimes in the textbooks is called differentiation using substitution, but that's basically using chain rule. And so differentiating u with respect to x is simple enough. It's 2x plus 5, and then differentiating y with respect to u is also simple enough, because it will just be 8u to the power of 3. And so the chain rule comes in and tells us that if you multiply du dx, so this is the differential of u with respect to x, if you multiply that by dy du, a chain reaction takes place, and in that chain reaction the du's will cancel, leaving you dy dx, which basically was what we wanted to do in the first place. We wanted to find the differential of y with respect to x. So du dx is this. So basically it would be 2x plus 5, and dy du is this, but of course we want to write this in terms of x, so therefore that would be multiplied by 8 times, and remembering that u was x squared, so u was x squared plus 5x to the power of 3. So really, nicely, if I wanted to just make everything written in the way that we expect to see them, like numbers in the front of the expression. So dy dx would be equal to 8 2x plus 5, which is the differential of the content multiplied by the content with 1 power less left. So when we are dealing with a g of x, let's get some extra pages here. So when we are dealing with a function of a function, so let's use the same idea to deal with a function of a function. So we are dealing with a function. So we say y is equal to a function g which is operating on fx. This, of course, can go to many levels. The composite function doesn't only have to be 2 functions; it could be a number of functions, and the chain can carry on. So it's so the chain doesn't, in this case, the chain only has 2 differentials that chain through, but that can be a number of them, and maybe we do this in the next video. So here I'm going to make a substitution, and so my u is going to take over the place of fx, and hence y would be equal to g of u now. So if I differentiate u, so it's du dx. Now du dx is the differential of this expression fx, which sometimes we show it with a little dash on the top. So the dash on the top of f basically means the natural differentiation of an expression of x, which we did something like this here. So for example, here we just differentiated this. So this is a expression written in x, and we differentiated it, and we got 2x plus 5. So f dash x basically is telling us that we are going to differentiate an expression of x, and that would be what we'll achieve eventually. And dy du would be the differential of g, well, the differential of g in terms of u, because that's what the subject of u is. So you would get a g dash u. So if we change these through, you would get du dx multiplied by dy du. That will change through, and the du and the du in this chaining will cancel each other out, and you will end up with dy dx. So really what dy dx is equal to is du dx, which is f dash x, and that's going to be multiplied by dy du, but dy du is g dash, but we don't want the u as a subject, so we just replace the u with what it was, where the u was in fact fx, so it would be g dash of fx. So as an example, if I wanted to just do an example of a composite function, let's just stick to something simple. So if, for example, we have an fx, which is, say, 3x cubed plus 5, and gx, let me write that again. So gx is equal to 2x squared plus 2. Then we know what g of fx would look like, and I can actually expand it, and I can really produce the function and then differentiate it. I can do that if I want to. But if we are differentiating g of fx, so if I am differentiating this, so let's say just put this inside a square bracket, and then put a dash there to tell us that we are going to differentiate it. So if I differentiate that, I expect to get the differential of f multiplied by the differential of g with fx in it. So let's suppose we actually want to work this out. So if we wanted to work this out, the differential of fx would be 9x squared, and the differential of g, so let's put a nice times here. The differential of g would be 4x, yeah, but this 4x, the x of it is going to be an fx, so it'll be 4 fx. Yeah, so that would be when you simplify it, that would be the final differential. Yeah. Now let's say we actually wanted to find the differential of g of x, but we wanted at a certain point. So let's say, for example, we wanted to find the differential of g of fx, but when x equals 1. So so the differential. So I'm just gonna write this slightly differently, so you guys can see all different ways of presenting this info. So I want to differentiate. G of fx with respect to x, and that would be the differential of fx. So I'll just write that the way we had it before: differential of fx multiplied by differential of g, but with the content of fx. And we want to evaluate this. We want to evaluate this when x equals 1. So when x equals 1, so if we go up there, when x equals 1, when x equals 1, f1 is equal to 8. I need that. I need f1. Then f dash 1. So the differential of this would be 9x squared. 5 will disappear. So f dash 1 would be 9. And then we need a g, but we need a g of when f1, when f is calculated for x being 1, and that was 8. So really we need a g dash of 8. So I need to calculate that as well. So g dash of 8, so this is g dash of 8. Well, the differential of g is 4x, and so times by 8 would be equal to 32. So really the differential of this, if we just use these numbers, the differential of this being evaluated at x equals 1 would be f dash 1. F dash 1 is 9 multiplied by g dash of 8, which was 32. So that's 270 and 18, so it'll be 288. Okay, I will do the composite functions of more degree of compositeness. So to more 3 or 4 functions being used to make a composite function, so you can see the chaining of a greater number of chains. We'll do that in the next video. If you like the videos, do please send me your questions, and I will do my best to make videos of them, make available to yourself and everybody else to use. And I'll see you in the next video.